Hey, what's going on, guys? Let's do this problem right here. The first question is asking an object that weighs 2.450 Newton is attached to an ideal massless spring and undergoes simple harmonic oscillations with a period of 0.6440 second. What is the spring constant of the spring? So they are asking for the K. They have provided the mg, the mass, the weight, that is equal to 2.450 Newton, right? That's Newton. And they have also provided the period t, that is 0.640 s. So when I see this, I remember the formula, that's t is equal to 2 phi square root of k over m, that is related to mass, period, and the constant. So the question is asking to find the constant. Here we have mg, so we have to find the m to apply in this equation. So let's calculate the m. M is going to be simply 2.450 divided by 9.81, right? 9.81. This is Newton, this is meter per second square. And if you calculate, you will get, this one comes out to be 0.25 kilogram. So we have the mass right now, and all we have to do is simply substitute, but let's get rid of the square root first. So this is going to be t square, that's going to be equal to 4 phi square k over m. We have to find the k, so let's bring the others to the other side. So k is going to be equal to t square m over 4 phi square, and t square, that's going to be this value right here. M is, we have 0.25 kilogram, and if you substitute all these values, you get 24.1 Newton per meter, and that is the last answer. And that is the answer for the first question. And let's do the second one. So we have, the question is asking, a 1.6 kilogram block on a horizontal frictionless surface is attached to an ideal massless spring whose spring constant is 190 Newton per meter. The block is pulled from its equilibrium position at x is equal to 0 meter to a displacement x is equal to 0.08 meter, and it is released from the rest. The block then executes simple harmonic motion along the horizontal x-axis. What is the velocity of the block at the time t is equal to 0.40? Okay, so they are asking for the velocity. Let's put the velocity to know what are the things we need, right? So let's put the velocity equation. So if velocity is going to be a minus a omega sine omega t plus phi, we don't have to put it because we don't have any shift right here. So this is going to be the equation. Amplitude, so they are saying this is released from the rest, and at the rest this was this height, so it means this is the amplitude. So amplitude is equal to, let's use a different color. Okay, amplitude is equal to 0.08 meter, and then we need to find the omega. That's not provided. We have the time is 0.4 second. So let's find the omega. Omega is equal to square root of k over m, and we have the k that is provided, spring constant 190, and mass is also provided, so we can simply find the omega. So let's substitute this one into this equation. This is going to be square root of 190 divided by the mass, that is 1.6 kilogram, and this is Newton per meter, this is kilogram, and if you calculate this one, you get let me see, yeah, that one comes out to be 10.9. So this one comes out to be 10.9. All we have to do is simply substitute in this equation. So let's substitute all the values. We have minus a is amplitude, that is 0.08, and then we have omega, that is 10.9 sine omega t, so 10.9 times t, that is 0.4 second. And if you calculate all these values, you will end up, because you're going to get a negative answer here. If you plug in the calculator, you will get a negative answer. This is just 0.4, because if I write unit, I have to write for everything, right? So here 0.4, and if you calculate this one, you will get a negative answer, since we have a negative in front of this one. So this is going to be negative, and you will get a positive answer. So the answer will become 0.82 meter per second. That's why we have to be careful, because they have provided the negative answers and the positive answer. The answer is positive, so this is the answer, right? And that's how it's done. And let's do the third part. So third part, they are saying a 0.25 kilogram ideal harmonic oscillator has a total mechanical energy of 4.0 joule. If the oscillator's oscillation amplitude is 20 centimeter, what is the oscillation frequency? So they have provided the mass right here, that's 0.25 kilogram. Mechanical energy, let's put E is equal to 4 joule. And we have the amplitude that's given in centimeter, let's put it in meter, that's 0.2 meter, right? And they are asking for the frequency. Okay, so whenever we have mass, I can remember this equation, like 1 over 2 pi square root of k over m, right? So that's the frequency equation. But we know the mass, we don't know the k. But they have given the energy and the amplitude. This means we can calculate this one using this formula. E is equal to half ka square. This is the maximum, like in the highest point. So that's going to be maximum potential energy, right? So here, that's going to be half, and we have that energy 4 joule provided. 4 joule is equal to half times k, that's what we are trying to find. Amplitude square, 0.2 square, and that's going to give us, if we flip round, k will become 8 over 0.2 square, and that gives us 200. So let's substitute all the values. 1 over 2 pi square root of 200 divided by 0.25 kilogram. And if you calculate this one, this gives you 4.5 hertz. And that's the final answer. That's the answer D, right? And that's how we do these kind of questions. I hope you guys like this video. See you next time.